Hello everyone, my name is Sonia Lamba. I am from ABES Engineering College, and in today's lecture we will discuss the various error detection methods. In previous lecture also we have discussed some of the methods, and those methods that are still remain we will discuss today. So today we will discuss the checksum error detection method and Hamming code, which is one of the error detection as well as error correction method with one example each. So if talking about the checksum error detection method, so checksum is also one of the error detection method that have been used for the error detection at the receiver's end. Checksum error detection method is more reliable than simple parity check, two-dimensional parity check methods. In this method, the data that the sender wants to send will be divided into the segments of each size. Let's say we have divided the original message into the subunits or segments of the n bits each, and at the sender's end all these segments are summed up together using one's complement, and once the summing procedure is completed, we will complement the sum, and this complemented sum is called the checksum. Now along with the data, sender will send the checksum also. Now at the receiver's end, upon receiving the data with the checksum, again receiver will follow the same steps. A receiver will sum these subunits along with the checksum using the ones complement sum method, and then after getting the sum, receiver will complement the sum using ones complement, and if after doing the ones complement we will get all the bits as zeros, it means the receiver has received the original frame. No error has occurred during the transmission, but if there is if the all bits are not zero, it means some during the transmission the frame has corrupted, and in that case receiver will simply discard the frame and then request for the retransmission of the frame from the sender side. Now we will discuss one example. Let's say the sender the data that the sender wants to send is 11010101. Let's say we have the two subunits. Another unit is 00110101. Each we have divided the data into two segments, two subunits, each of size 8 bits, each of size 8 bits. Okay, so now the process of checksum will start at the sender's end. Here right now we are discussing the sender's end, and then we will discuss at the receiver's end. So this is the data which was divided into two segments, each of size 8 bits. Now we will sum these two segments using ones complement. Now 1 plus 1 is 0, carry will be 1. Now this is 1. Now again 1 plus 1 is 0, carry will be 1. This is 1. 1 plus 1 is 0, carry is 1. 1 plus 1 is again 0 here, carry will be here. 1 plus 1 is again 0, then carry will be here, and 1 plus 1 is again 0, and this is your carry. Now after summing these two segments using ones complement, we are getting one extra bit. Now we need to perform the procedure of wrap sum here. So in wrap sum we will pick this bit 1 with this extra bit, and will add this bit at the right hand side using again one's complement sum. So here we will get 1 1 0 1 0 0 0 0. So this is now this is the sum after wrap sum and after adding the segments together using one's complement. Now we need to perform the one's complement of this sum. this wrap sum. Now doing the ones complement, in ones complement the bit which is 1 will become 0 and the bit which is 0 will become 1. So 1 here, so we will get 0 0 1 0 1 1 1 1. So this is the checksum. This is the calculated checksum at the sender's end. Now, when the sender will send the data, let's say this is the data 1 1 0 1 0 1 0 1 and 0 0 1 1 0 1 0 1. Now this is our data that the sender wants to send, and this is the calculated checksum. So along with data, sender will send the checksum as well. So checksum is 1 1 1 1 0 1 0 0. This is our checksum. Sender will send us. Now let us assume that because the channel was idle, no error has occurred during the transmission. Receiver has received the original frame along with the checksum. So now how the receiver will detect whether the receiver has received the original frame or the receiver has received the corrupted frame. So again, along with the data, receiver will add the checksum part as well. So here again we will use the ones complement sum method. So 1 plus 1 here is 0 and carry will be 1. So here we will get 1. Now 1 plus 1 plus 1 is 3. So 1 will be here, 1 will be the carry. Now carry this one. 1 for 1 plus 1 plus 1 again 3. 3 means 1 1. It means 1 will be here, 1 will be the carry. Again 1 plus 1 is 3. So 1 will be here, 1 will be the carry. Again 1 plus 1 is 1. 3. 3 means 1 1. So 1 will be here, 1 will be the carry. 1 plus 1 is again 1 and 1 will be the carry. So we will get here. Again, one extra bit generated. So, but we need to keep the segment of 8 bits only. So we will pick this pick and will add at the right hand side. Now this is called wrap sum. So after getting the wrap sum, we will get this 1 1 1 1 1 1 1 1. Now this is the wrap sum. Now we will do the ones complement of the sum. So when we will do the ones complement, we will get all 8 bits as zeros. 1 2 3 4 5 6 7 8. So when at the moment you will get all the 8 bits as zeros, it means no error has occurred during the transmission and receiver has received the original frame. So this is the method of checksum, and this is the way by which user will be able to detect the errors at the receiver end. This method is more reliable comparatively to simple parity check as well as to the two-dimensional parity check. So this is one of the example of checksum. Now we will discuss the another error detection and correction method. So Hamming code is error detection as well as error correction method. One bit error can be can be corrected with the help of this Hamming code method. This is the method and developed by R.W. Hamming for error detection as well as correction purpose. So till now, all the methods that we have discussed, all methods are error detection, but Hamming code is the error correction method as well. But only one bit error can be detected, can be corrected with the help of this Hamming code method. So in case of the Hamming code error detection method, we need to calculate the redundant bits that the receiver that the sender will append with the data and will send to the receiver. So redundant bits are nothing. These are the extra bit added to the data part for error detection and correction at the receiver's end. Based using these redundant bits, receiver will be able to identify at the receiver end whether the error has occurred or not. So this is the formula for calculating the number of redundant bits. So M here is the size of the data and R is the number of redundant bits required. So this is the formula via which we can calculate the number of redundant bits if the size of the data is M. Now we will discuss how the redundant bits are calculated, and how where we will place these redundant bits. So redundant bits are always placed at the powers of 2 only. Okay, you need to remember this point. It is very important point. Redundant bits are the extra bits that are appended by the sender, but sender cannot randomly append these bits. These bits are always appended at the powers of 2 only, at the position of powers 2. So for example, we will consider one example as well. Let's say size of the data is m number of bits are there in the data. So as per the formula says 2 to the power r greater than equals to m plus r plus 1. Here the size of the data is m, we can say 7 plus, we need to calculate the number of redundant bits, how much redundant bits need to be appended with this size of data. So we need to place this value at r. So if we will place here the 3, so 2 to the power 3 is greater than 7 plus 3. 7 plus 3 is 10 plus 11. So condition not satisfied, it means r cannot be 3. So as per the formula, we need to increase this value of r, m plus r plus 1. So size of data is, original data is 7 plus, if we will place the value of r as 4, so we will check whether the formula is satisfied or not. So 2 to the power 4 is 16. 16 is greater than equals to 7 plus 1 is 8, and 8 plus 4 is 12. So now the formula has satisfied. It means we need to keep the redundant bits as 4. So redundant bits that need to be appended will be 4. But now the point is where we will need to place these redundant bits. So redundant bits are always placed at the powers of 2. First bit, redundant bit will be placed at 2 to the power 0, which is equals to 1. Second redundant bit will be placed at 2 to the power 1, which is equals to 2. Next, third redundant bit will be placed at the power of 2 to the power 3, which is equals 2 to the power 2, which is equals to 4. And the fourth redundant bit will be placed at the 2 to the power 3, which is equals to ace. So these are the position where we will place the redundant bit. So first redundant bit will be at 1 position, then second will be at 2, third will be at position 4, and the next fourth bit will be at the position 8. So this is how we can calculate the number of redundant bits that need to be appended with the data part, and where we will place these redundant bits. Now, we will discuss the method of Hamming code, error detection and correction method, with the help of one example. So this is our data. So first we calculate the size of the data. So size of data is 1, 2, 3, 4, 5, 6, 7. Data m is 7. So first we need to calculate the redundant bit. So as per the formula, 2 to the power r greater than equals to m plus r plus 1. Redundant bits will be 4. So now we also know that redundant bits are 4, and we always place these redundant bits at the powers of 2. So we will place these redundant bits at position 1, at 2, at 4, and then at position 8. So we will design the one box. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So this is our code word. So after adding the redundant bits into the data word, the data word will become code word. So this is our code word. Now we all know that redundant bits are always added at the position of 2 only, at the powers of 2 only. So this is the place where we will put the redundant bit 1. Here we will place the redundant bit 2. Here we will place the redundant bit 3, and at the position of 8 we will place a redundant bit 4. Now we all know we have the data right now. At rest of the position we will place the data part. So data is 1, 0, 1, 1. Sorry, here we are not going to place anything. because this is the redundant bit position. 1011. So till now we have placed the bits of the data at the particular location, and we have identified the location of the redundant bits as well. Now we will calculate these redundant bits value for these redundant bits. So let us say first we will start with R1 redundant bit 1. So for calculating the value of this redundant bit 1, we will start with 1, and then we will skip one value and then 3, 1 3, then we will skip one value 4 and then 5, then we will skip 6 and then 7, then we will skip 8 and then 9, then we will skip 10 and then 11. So we have till 11 only in code word, so we will move till 11. So at one position we don't know what should be there, so but at position 3 we have this value 1. Now at position 5 we have this value as 0. At position 7 we will have 1, and at position 9 we have 1, and at position 11 we have 1. So because we are using the even parity, so we need to keep the number of ones as even. So again we will calculate the number of ones. So here number of ones are already even. So the value of this redundant bit R1 should be 0. Now again, we will calculate the redundant bit R2. So for calculating the redundant bit R2, we will start with 2. We will take two values 2, 3, and then we will skip 4, 5, and then we will take 6, 7, and then we will skip 8, 9. Then we will take 10 and 11. We will start with 2, we'll skip 2 again. So at 2 position, we don't know what should be there, but at 3, we know here it is 1. At position 6, the value is 0. At position 7, the value is 1. At position 10, the value is 0. At position 11, the value is 1. So we need to keep the number of ones even, but here the number of ones are odd. So at this place 2, we need to keep the value as 1. So here we will place 1. Now again we will calculate R3 as well. So for R4, sorry, R4. So for R4, redundant bit 4, at which is placed at 4, we can say redundant bit 3, but this redundant bit will be placed at fourth location. So for this we will start with 4, 4, 5, 6, 7, 8, 9, 10, 11 will be skipped here. Now at position 4, we don't have the value right now. At 5, we have the value 0. At 6, we have value 0. And at 7, we have the value 1. So now the number of ones are odd. So we need to keep the number of ones even. So value of 4 will be 1. So here we will place value at 1. So now again, we will calculate the R8 or the redundant bit 4. Redundant bit at 8 position, or we can say the redundant bit 4. So for R8 calculation, we will start with 8, 9, 10, and 11. We will take 8 bits, first 8 bits, and then we will skip next 8 bits. So right now we have only 4 bits, so we will take that 4 bits only. So 8 pay, we don't know what should be the value. At location 9, we know here it is 1. At location 10, the value is 0, and at location 11 the value is 1. So number of ones are already even, so value at location 8 will be 0. So here we will place the value as 0. So this is the code word that we have calculated based on the even parity using the Hamming code. So sender will send this code word to the receiver. Now upon receiving this data, at the receiver's end, receiver will again follow the same process and will try to detect the error. So let us check again how the receiver will detect the error. Let us suppose that the sixth bit has been changed during the transmission from 0 to 1. And now we will check how the receiver will detect this error and then will correct this error as well. So this is the code word that has been sent by the sender, and during the uh, transmission, the sixth bit was originally calculated was 1, but during the transmission this bit has been changed from 1 to 0. And we will see now key how the receiver will be able to identify which bit has been corrupted during the transmission, and will receiver will able to correct this error as well. So first we need to detect the positions at which places we have put the redundant bit. So this is our redundant bit 1, redundant bit 2, redundant bit 3, and redundant bit. This is our redundant bit 4. Now again, at the receiver's end, based on the code word received, receiver will calculate the redundant bits again. So for calculating R1, once I start करेंगे, 1, 2 को skip किया, 3, then 4 को skip, 5, 6, 7, 8, 9, 10, 11. So for calculating R1, we will start with 1, we'll take one bit and we'll skip another bit. So at position 3, we have 1. At position 5, we have 0. At position 7, we have 1. At position 9, we have 1. At position 11, we have 1. And at position 1, we have 0. So we need to keep again the number of ones even. So already the number of ones even. So R1 will be 0. Now again, we will calculate R2, 2, 3, 4, 5 skip, 6, 7, 8, 9 skip, 10, 11. So at position 2, we have 1. At 3, we have 1. At 6, we have 0. At 7, we have 1. At 10, we have 0. At 11, we have 1. So number of ones are already even. So again, value of R2 will be 0. Now, we will calculate R4. Start with 4, 4, 5, 6, 7, 8, 9, 10, 11 will be skipped. Take 4 bits and next 4 bits you need to skip. Now at position 4 we have 1, at 5 we have 0, at 6 we have 0, at position 7 we have 1. So number of ones are already even. So again, we were calculating the value for R2. So here we can see the number of ones are already even. It means R2 is also correct. So R2 value is 1. It is correct. Actually, we need to check here whether the value of redundant bit is correct or not. So next we will calculate R4. So for R4, we will start with 4. We will take 4 bits, 4, 5, 6, 7, and then skip next 4, 8, 9, 10, 11. So the value at location 4 is 1, at location 5 is 0, at location 6 it is 0, at location 7 it is 1. So here also number of 1 should be even, number of ones are already even. It means R4 is also correct, R4 value should be 1. So we have also calculated for R4. Next we need to calculate R8 as well. So we'll start with 8, we'll take 8 bits, 8, 9, 10, and 11. So value at location 8 is 0, bit at location 9 is 1, at location 10 it is 0, at location 11 it is 1. So number of ones are already even, it means R8 is also correct. So R8 should be 0. So here we have calculated the bit values for R1, for R2, for R4, and for R8. At R1, it should be 0. At R2, it should be 1. At R4, it should be 1. At R8, it should be 0. Now, we will write these bits like this. We will read it like this from bottom to top. 0, 1, 1, 0. And we need to calculate the decimal value of this. So decimal value of this is 6. So this is how a receiver will be able to detect and the correct the error. So receiver has detected that the bit has been changed at location 6. So right now receiver will simply change this bit value from 0 to 1. So receiver has detected the location of the bit also where the change has occurred during the transmission. So using the Hamming code error detection and correction method, we can detect the location of the bit as well. But in the rest of the methods, we can only detect the error, whether the error has occurred or not. But in Hamming code, we can detect the location at which the bit has been changed, and but only one bit error can be detected with the help of error Hamming code error detection and correction method. So that's all for today's class. Till now we have discussed or the 4 5 methods of error detection and correction. These are the references. Thank you everyone for a patient learning. Thank you.